We're back.
We're back. Welcome back, guys. So we're picking up where we left off with heat capacity. So we're still in 6.4. And what we're going to do today is a little bit of an experiment. So just a reminder, get my pen here. Specific heat is the amount of energy required to raise 1 gram of a substance 1 degree Celsius. Mm-hmm. So if I think about this, what would heat faster if I had 10 grams of aluminum or if I had 10 grams of wood?
Depends on the specific heat.
Depends on the specific heat. Well, metal, we all know metal gets hot pretty fast, right? That's why we don't touch the pot on the pan. I mean, if you're cooking something, I should stop. I'm blabbering on here.
A little bit, but that's okay. Keeps it interesting.
So, let's go ahead and look at this. Heat capacity. Well, how do we calculate it? Well, what we're going to do is you're going to see an experiment. Miss Morris is going to carry it out where we are going to determine the heat capacity of a metal.
And the way that we're going to do that is that we're calculating the energy that's lost by the metal, and we're equating that to the energy that's gained by the water because we can measure that.
So we're going to heat up a metal, and then we're going to dunk it in some water. We're going to see what the temperature changes in the water, and then we're going to assume all that energy that left the metal
goes right into the water and nowhere else.
And then we have a calculation for that.
Yep.
So let's go ahead to the experiment.
All right. What we're doing today is trying to figure out the identity of a metal based on calorimetry and based on the heat lost by the metal and the heat gained by the water. So what we're actually doing is we're trying to get the initial temperature of the water. Is what we're going to do is we're going to take the metal that's heating up in here. It's really reaching the same heat as the water. We're going to put it into the cooler water. Okay? Keeps moving. Let's say 24.3. All right, and we're going to measure the heat difference.
And that's the temperature of the...
Temperature of the cooler water. The temperature of the metal that we're going to take, we're actually going to measure the water around it. Where it's going up. So it's easier for us to measure the heat of the water than it is for us to measure the heat of the metal. We're going to say that it's equilibrating. All right, 86.3.
Okay, so we have the temperature of the metal is 86.3 and the water is 24.3.
Yeah. So what I'm going to do now is I'm going to use my forceps. I'm going to transfer the metal from the heated water to the normal water. We're going to go ahead and we're going to measure the heat change of that. The name of the game is to not burn myself.
Okay, so while Miss Morris is turning that, we'll see if we can get the temperature reading as well.
26.
So kind of stir it as you go.
Rolling for when it goes down.
Trying to find a temperature of where it stays still. It's looking 25.17. It's all over the place. We're looking at the red one.
So I'm going to give it some time.
And maybe, is it still jumping?
It is.
There we go. Let's see if it settles. Maybe 25.2, 25.3.
I'm thinking 25.3. Shut up there a couple times.
It stays. It looks like it's staying. Whoa, there it goes again. There, settling a little bit. Maybe 25.0 is where it kind of settled out.
Yeah. Yep.
Okay, so we'll go ahead and, I think it's 25.0, so we'll come back and...
So, the final temperature of that water is actually going to be the final temperature for both of ours. So both the water and the metal. So I had to fill in 25.0 degrees Celsius.
So we're pretending all the heat that that was lost by the metal.
Was the same amount of heat that was gained by the water. Because remember, nothing's actually gained or lost. We lost a little bit to the air, but we're not going to count that into our calculations because we're going to consider it a perfect system.
Okay, so let's go ahead and calculate it.
All right.
So I'm going to split my side here. Let's write down our knowns from the experiment.
Okay.
So let's do the H2O side.
H2O being water.
And the metal side. And we don't know what this metal is. Well, we know, but we gotta figure out what it is. So the first thing was our mass of water, and we put how much?
100 grams.
100 grams.
We actually put 100 milliliters, but we do a conversion to get 100 grams.
And the initial temperature of that water?
24.3 degrees Celsius.
24.3 degrees Celsius. And the final?
25 degrees Celsius, 25.0.
25.0 degrees Celsius. And our metal, how much? We didn't weigh that at the end, but you, after we clicked off the video, she went and weighed it. And the mass of the metal?
8.9 grams.
Was 8.9 grams. And the initial temperature of that water that it was sitting in?
Initial temperature of the water it was sitting in was, looking over, 86.3 degrees.
86.3 degrees, and this is in Celsius. And remember, we assumed that the temperature final was the same, that they equilibrium. We waited until they evened out. Oops, that's not what we want. Oh well, I didn't mean to erase all of that. So what we're going to do is we are going to do the heat capacity for water. We know the heat capacity of water. That is 4.18 joules per grams degrees Celsius. And we don't know the heat capacity of the metal.
But we can figure that out.
That's what we're going to measure. So let's go ahead and set up our equations. You remember our heat capacity equation?
Yeah, I remember with Q equals MCAT, so it's Q equals M, C, and then delta T.
And I put P here. I'm in the habit of that. That's the same thing. C, you'll see us do C or CP. They both mean specific heat capacity. Times delta T. And that is for our water. So this is all for our water. And we're going to have Q of the metal is going to equal some mass of the metal times the specific heat of the metal times delta T.
Yep.
Oops. Back. Times delta T. So let's go ahead and do the first one. These should be...
And we are just plugging them in, so they should be equal.
They should be equal. So I don't have much room here, but I'll see if I can squeeze it down below. So Q of the water, we have for our mass was 100 grams. 100 grams. Sorry, guys.
So writing your labels is actually going to be really important so everything can cancel out.
So we've got 100 grams. And our specific heat is 4.18 joules in grams and Celsius are on the bottom. And our change in temperature, well, this is going to be T final minus T initial. So this will be 25.0 degrees Celsius minus 24.3 degrees Celsius. So let's go ahead and do that in our calculators. Okay, so I'm going to go ahead and plug this in. We've got 100 grams. Oops. And we are going to 100 grams times our heat capacity, which is 4.18, times our temperature change, which was 25 minus 24.3.
Now you don't need the parentheses for the 100, the 4.18, but you definitely need them for that 25 minus 24.3.
Right, so I get 292.6. So if I come back over to my equation, I've got 292.6. And the units for this are joules, because my grams cancels with the grams on the bottom, and my Celsius cancels with the Celsius bottom. All I'm left with is joules. So 292.6 joules was absorbed by the water. So we're going to now set that equal to the energy that was lost by the
Yep. So
metal.
let's write that number up and then clear our space.
Okay, so here's what we're given. We know that this was the energy gained by the water. So we're going to set QW equal to the QM. So now I'm going to take QW and I'm going to substitute it into this equation because they should be the same. Heat loss should equal heat gained. So I'll have Q 292.6 joules, and that's my QM, equals my mass,
which is 8.9 grams.
Q, and my CP, which I don't know, that's what I'm solving for.
So we're going to leave that CP in there like our variable.
And T final minus T initial. Now this should be negative of one another, so it's actually...
Because one was gained, one was lost,
yeah,
that loss is a negative.
So the negative shouldn't be too big of an issue, but I'm going to have 25.0 minus 86.3 degrees Celsius. Okay, so I've got to get CP by itself. So the first thing I need to do is I'm going to, first of all, I'm going to solve this out. Can you help just plug that in a calculator? I have to bring that up again.
Negative 61.3.
Okay, and that negative that's here is going to cancel with this negative here. So when you do this in lab, you're just going to forget the negatives. And you got 61.3 degrees Celsius. So this is equal to 292.6 joules. Now what we have is we've got this number and this number here. In order to get CP by itself, I'm going to go ahead and just divide to the other side.
Because the opposite of multiplying is dividing.
Exactly. So I'll put 8.9 on the bottom, 61.3 on the bottom, and whatever I do on one side,
we do on the other.
Got to do on the other. And this is going to cancel. This is going to cancel. And what do we get for our heat capacity?
We're working on it.
I'll go ahead and write the units. I can see the units is going to be joules divided by grams in degrees Celsius. 0.54. And that is actually a pretty reasonable capacity. So if we go back to our chart, let's go ahead and go back to our chart. So remember, we got 0.54 for our heat capacity of the metal. And if we go and look at our chart, well, anything that seems close to 0.54?
Not quite.
Not quite. Somewhere in the middle of here. It's actually what we did, we're a little bit off. We're a little bit off. So we had iron, and we estimated about 0.54, and we're pretty close.
Yeah.
Pretty close. So we know it's not granite, that's too high, and copper's a little bit lower. So in our experiment, we were probably, 10%, 10% off.
And if you really want to go ahead, we'll show you how to calculate percent error.
Yeah, we can do that later. So, and you actually do that in your lab.
Cool.
Come ready to discuss what is specific heat tomorrow. That'll be your CFU for the day, and talking about your check for understanding is, can you describe specific heat? What would be a higher specific heat for one material versus another material?
And what's one way to compare it?